Okay, children. So we started with the basics of thermodynamics, in which we learned about the first law, second law, third law, and also zeroth law. Now we'll just revise what are all those, what is thermodynamics, and then what are the entities involved in this thermodynamics in view of your syllabus. So let us start with our...
Hello everyone, I'm Dr. Hemabindu, working as Assistant Professor. The objectives of this module are to understand the concepts of thermodynamics, to understand its significance in physics and daily life, to understand the difference between heat and temperature, to get the knowledge about heat transfer and heat engines, learn the basic laws of thermodynamics and their applications in their daily life, learn the thermodynamic processes with examples. Let us define the word thermodynamics. In 1749, William Thomson coined the term thermodynamics. This word was derived from two Greek words, thermis, which means heat, and dynamikos, which means powerful. Thermodynamics is the study of the effects of work, heat, and energy on a system. It deals with temperature, heat, and their relation to energy, radiation, work, and properties of matter. The energy can be of any forms such as electrical, mechanical, or chemical energy. As the definition of thermodynamics involves heat, let us now see what is heat. Heat is energy that is transferred from one body to another as a result of difference in temperature. Heat always flows from hot body to cold body and never flows backwards. How do we know whether a body is cold or hot? Can we touch and check? Yes, for few objects. But our skin has a sensitivity which is limited for few hot objects and for few cold objects. How do you understand hot or cold? If any object is at a greater temperature than our normal temperature, then we feel it as hot. And a body which is at a lower temperature than our body, we say it is cold. And hence, temperature is always a measure of hotness of a body. The units are centigrade, Celsius, Kelvin, Fahrenheit. You can see an example figure of feeling hot or cold. If you stand in hot sun, you start feeling terrible. And during winters, when the temperature is below 5 degrees, then also you feel terrible. But there is a temperature difference, and lesser the temperature, you feel more cold. Greater the temperature, you feel more hot. As we know that heat is a form of energy, how does this energy transfer? There are mainly three types of heat energy transfer: conduction, convection, and radiation. In heat conduction, energy is transferred from molecule to molecule by direct contact. The molecules themselves do not necessarily change position, but simply vibrate more or less quickly against each other. Convection is the transfer of heat by the movement of fluid, which is a liquid or a gas, between areas of different temperature. Warm air is less dense than cold air, and so convection currents can form in the presence of a temperature gradient. Radiation is a method of heat transfer that does not rely upon any contact between the heat source and the heated object. Heat can be transmitted through empty space by thermal radiation. To explain this, look at the figure. There is a vessel containing water. And when you start heating it, there is no direct contact between flame and the vessel. But yet, through radiation, the vessel gets heated. And the vessel starts heating up because of the process conduction, whereas the water inside it heats up through convection, where the molecules move up and down. So this simple experiment explains all the three types of heat energy transfer in other than using in the kitchen for cooking. Is there any application of heat? Yes, the major applications are heat engines. Heat engines play a pivotal role after industrialization. What are the components of this heat engine? Let us see. A heat engine involves a process which converts heat energy into mechanical work. There are three main parts in an engine: a heat source, a working substance, and a sink. The source of heat is of infinite thermal capacity, and that should be at a constant high temperature, so that if any amount of heat is withdrawn from it or given to it, it does not affect its temperature. A working object is something through which the heat is absorbed or rejected into the sink. Sink must be of finite thermal capacity, and that should be at a constant low temperature than the source, so that if any amount of heat is withdrawn from it or given to it, it does not affect its temperature. Perfect example of a heat engine is a steam engine. Steam, which is at a greater temperature, is utilized by this engine to move. So here we can see that the heat energy is transformed into mechanical energy. Let us look into the term specific heat capacity. You can see here there are two pots. One is a steel pot, the other is a clay pot. If you want to cook food in any of these pots, what do you expect? Which pot cooks food at a lesser time comparatively? Obviously, it is the metal pot or the steel pot. The reason for this is the specific heat capacity. Clay has high heat capacity and hence requires more heat to cook food. Metals have lesser heat capacity compared to clay, hence the food cooks quickly in metal pots. While heating any substance, to increase the temperature of the substance, the molecules have to vibrate. For this, the bonds between atoms have to be broken. More the bonds, more heat is required to raise the temperature of that substance. Similarly, for the substance to cool down, it takes a bit of time. As heat is dissipated, temperature decreases and the vibrational moment of molecules in the material slows down. The heat that is given off counteracts the cooling effect of the loss of heat from the substance. Thus, we can define specific heat as the amount of heat per unit mass required to raise the temperature by 1 degree centigrade. The relationship between heat and temperature change is usually expressed in the form shown below, where C is the specific heat. Now it's time to learn about the laws of thermodynamics. There are 4 laws of thermodynamics: the zeroth law, first law, second law, and third law. Zeroth law gives us an insight into thermal equilibrium of bodies. Look into the figure. There are 3 bodies, namely A, B, C. The temperatures of A, B, C are T1, T2, T3 respectively. If the temperature T1 of A is equal to the temperature T2 of B and temperature T2 of B is equal to temperature T3 of C, then The temperature of A and temperature of C are both equal, that is T1 is equal to T3. In other words, A and B, which are in thermal equilibrium with each other, and B and C are in thermal equilibrium with each other, then A is also in thermal equilibrium with C. This law explains that temperature always exists, and in thermal equilibrium, temperature of all the bodies remains same. First law of thermodynamics tells about the internal energy of a system. Let us see how the internal energy changes with the supply of heat. Consider a glass beaker with some gas and a stopper at one end. Now, when an amount of heat Q is supplied to the system, the internal energy U1 of the system changes to U2, and also the gas expands, moving the piston upwards. So the movement of this piston is the work done by the system. Now, the first law of thermodynamics is actually law of conservation of energy, stated in a form most useful in thermodynamics. The first law gives the relationship between heat transfer, work done, and the change in internal energy of a system. Experiments prove that delta U is equal to Q minus W, where delta U is the change in total kinetic and potential energy of all atoms and molecules in a system. Also, the internal energy U of a system depends only on the state of the system and not how it reached that state. U is a function of a few macroscopic quantities like pressure, volume, temperature, etc. Let us consider a system in which the molecules are arranged properly and the orderedness is very high. If we start heating the system, the temperature of the system rises. But not only that, the atoms or molecules inside the system start vibrating and they move randomly. And the orderedness changes to disorderedness. This disorderedness in thermodynamics is termed as entropy. The amount of heat supplied turns into both temperature and another term, entropy. The second law of thermodynamics says that the entropy of an isolated system always increases. Isolated systems evolve towards thermal equilibrium, which is the state of maximum entropy of the system. In other words, the entropy of the universe, which is the ultimate isolated system, always increases and never decreases. Look at the left-hand side of the figure. It shows the arrangement of molecules at a higher temperature, which are more unstable. But when the temperature moves towards absolute zero, the entropy of the system decreases, which is the example of a crystal. A crystal which is at a low temperature has a low entropy and is more stable, or you can say it is in equilibrium. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, its entropy becomes constant, or the change in entropy is zero. The third law of thermodynamics predicts the properties of a system and the behavior of entropy in unique environment known as absolute temperature. Let us now try to understand the thermodynamic processes. Look at the figure. We see ice and water. We can convert ice into water and also water into ice. But by doing some work, we supply some amount of heat to ice to turn it into water and remove heat, then it becomes ice. So there is some work involved in this. It's not a spontaneous process. A reversible process is a process in which the system and environment can be restored to exactly the same initial states that they were in before the process occurred if we go backward along the path of the process. The necessary condition for a reversible process is therefore the quasi-static requirement. Note that it is quite easy to restore a system to its original state, but the hard part is to have its environment restored to its original state at the same time. In the example of an ideal gas expanding into vacuum to twice its original value, we can easily push it back with a piston and restore its temperature and pressure by removing some heat from the gas. The problem is that we cannot do it without changing something in its surroundings, such as dumping some heat there. Look at the image here. We see wood burning into coal and then ash. Can this be reversed? Absolutely, we cannot. An irreversible process is what we encounter in reality almost all the time. The system and its environment cannot be restored to their original states at the same time. Because this is what happens in nature, it is also called a natural process. The sign of an irreversible process comes from the finite gradient between the states occurring in the actual process. For example, when heat flows from one object to the other, there is a finite temperature difference, which we call it as gradient, between the two objects. More importantly, at any given moment of the process, the system most likely is not at equilibrium or in a well-defined state. This phenomena is called reversibility. Examples are all chemical reactions and all natural processes. From the PV diagram, it can be seen that a reversible process is a fast process, whereas a reversible process is a very slow process. There are two important conditions for the reversible process to occur. Firstly, the process should occur infinitesimally small time, and secondly, all of the initial and final state of the system should be in equilibrium with each other. During the irreversible process, the various states of the system on the path of change from initial state to final state are not in equilibrium with each other. The entropy of the system increases decisively and it cannot be reduced back to its initial value. Let us see the other thermodynamic process: isobaric, isochoric, isothermal, and adiabatic. Isobaric process occurs at constant pressure, and the equation is W is equal to P delta V. Since W is the work, P is the pressure, and delta V is the change in volume, there would be two possible outcomes to an isobaric process. If the system expands, then the system does positive work. If the system contracts, then the system does negative work, where the pressure is always a positive value. In isochoric process, which is at constant volume and the work done is equal to zero, it means the system does no work. This is perhaps the easiest of the thermodynamic variables to control, since it can be obtained by placing the system in a sealed container which neither expands nor contracts. In an isothermal process, the temperature of a system remains constant. The transfer of heat into or out of the system happens so slowly that thermal equilibrium is maintained. An adiabatic process is one in which no heat is gained or lost by the system. It means Q is equal to 0. The best way to represent isothermal and adiabatic process is a Carnot cycle. A Carnot cycle is defined as an ideal reversible closed thermodynamic cycle in which there are four successive operations involved, and they are isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression.
These are the books that you can read for whatever I have told you. So you have Engineering Thermodynamics by P.K. Nag, and Thermodynamics by S.C. Gupta, Engineering Thermodynamics by R.K. Rajput, Heat, Thermodynamics and Statistical Physics by Brijlal Subramaniam and Hemne, then Thermodynamics by C.P. Arora. So any of the books you can check out, and also you can check out the online class which I have shared with you on Coursera, and then that will help you, I suppose.